Automobile engines, a comprehensive guide. The automobile engine is the heart of every vehicle. Its primary function is to convert the chemical energy of fuel into mechanical energy that drives the wheels. While most modern vehicles use internal combustion engines ICE, electric and hybrid motors are increasingly changing the traditional approach to propulsion. #1. How engines work. The classic engine is the four-stroke piston engine which operates through 4 phases. 1. Intake The piston moves down, drawing in a mixture of air and fuel into the cylinder. 2. Compression. The piston moves up, compressing the mixture and preparing it for ignition. 3. Power/combustion stroke. The mixture ignites, pushing the piston down and creating mechanical energy. 4. Exhaust The piston expels the burnt gases from the cylinder. The engine converts the linear motion of the pistons into the rotational motion of the crankshaft, which drives the transmission and wheels. #2. Engine components. Engines consist of several key parts. Cylinders and pistons, the space for fuel combustion. Pistons are usually made of aluminum or steel, balanced for smooth operation. Crankshaft made of hardened steel, converts linear motion into rotation, precisely balanced. Cylinder head and valves control the intake of air, fuel, and exhaust flow, including variable valve timing systems, VVT. Spark plugs/injectors ignite the mixture or inject fuel precisely. Oil pan and lubrication system lubricates all moving parts, reducing friction and heat loss. Radiators and cooling system regulate temperature, prevent overheating. Sensors and control units monitor temperature, pressure, valve timing, pump operation, oil pressure, emissions, and more. #3. Manufacturing process. Engine production is a highly precise engineering process. Casting and machining engine blocks aluminum or cast iron blocks and heads are processed with CNC machines with tolerances of tenths of a millimeter. Making pistons, crankshafts, and valves, hardened steel, balanced, and vibration tested. Engine assembly, precise installation of valves, pistons, bearings, and other components. Testing and calibration, power, fuel consumption, emissions, and vibration tests. #4. Modernization and improvements. Engines are continuously improved for higher efficiency and lower fuel consumption. Turbochargers and variable turbochargers increase power without increasing engine size. Direct fuel injection and smart injection systems precise fuel delivery, lower consumption and emissions. Downsizing plus turbo, smaller engines with turbo for power and efficiency. Exhaust gas recirculation, EGR, reduces NOx emissions. Catalytic converters and particle filters control emissions and protect the environment. Hybrid systems combine ICE and electric motors for lower fuel consumption and emissions. #5. Electric and hybrid motors. Electric motors simple construction, minimal maintenance, instant torque, zero emissions during driving. Hybrid motors combine internal combustion and electric motors, enabling economical city driving and longer range. Batteries and management systems crucial for electric and hybrid engines, including advanced cooling and charge cycle monitoring. #6. Common failures and problem prediction. Engines with high mileage may develop loss of compression, worn piston rings, gaskets. Cooling issues, blockages, water pump failure. Worn valves and cylinder head gaskets. Fuel injection and ignition problems. Vibrations due to imbalance or worn crankshaft. Modern vehicles use sensors and computer diagnostics for early problem detection and preventive maintenance. 7. Future and innovations. Electrification, transition to fully electric drives. Ice optimization ***, smaller engines, turbocharged, lighter materials, reduced friction. Automated production ***, robots and AI for maximum precision and cost reduction. Reduced maintenance costs. Electric motors require almost no oil or belts. Preventive monitoring becomes standard. #8. Maintenance costs. Gasoline diesel engines **, 201,000 euros per year, depending on mileage and model. Hybrid engines **, lower costs due to reduced ICE usage. Electric engines **, minimal costs, except for battery replacement, 8–15 years, while other components rarely require service. Evo professionalnog Ingelskog Prijvodativodig teksta, spremnog zaprit vorbu u audio, estechnym, narrativnym stylem. 1. How an automobile engine works, detailed explanation. An internal combustion engine operates on the principle of converting the chemical energy of fuel into mechanical work. This process is based on the controlled combustion of a mixture of air and fuel within a confined space, the cylinder. When the mixture ignites, there is a rapid increase in pressure and temperature, creating a force that pushes the piston downward. The piston moves along a precisely defined axis within the cylinder, with minimal tolerances. This linear motion is transmitted through the connecting rod to the crankshaft, which then converts it into rotational motion usable for driving the vehicle. An engine does not operate in a single continuous step, but rather through clearly defined phases. In a four-stroke engine, these phases are intake, compression, combustion, and exhaust. During the intake phase, the valve opens to allow air or an air-fuel mixture into the cylinder. In the compression phase, the valves are closed, and the piston compresses the mixture, raising its pressure and temperature. In gasoline engines, a spark plug ignites the mixture, whereas in diesel engines, ignition occurs solely due to high pressure and temperature. The resulting combustion is not an uncontrolled explosion, but a fast, controlled burn. This combustion produces the majority of the engine's useful energy. Afterward, the exhaust phase occurs, where the piston pushes the burned gases out of the cylinder through the exhaust valve. This cycle repeats thousands of times per minute. The engine's revolutions per minute, or RPM, directly influence its power output and fuel consumption. Heat management is another critical aspect of engine operation. Much of the fuel's energy converts to heat, with only a portion transformed into useful mechanical work. Therefore, engines require an efficient cooling system to prevent overheating. Additionally, friction between moving parts must be minimized through lubrication systems. Without oil, the engine would fail rapidly. Balance and synchronization are also essential. Valves, pistons, the crankshaft, and the camshaft must operate in perfect coordination. Even minor deviations in valve timing can lead to power loss or serious engine damage. Modern engines use precise sensors and electronic control units to continuously adjust engine operation based on driving conditions. Finally, it is important to understand that an engine is not an isolated system. It constantly interacts with the transmission, exhaust system, cooling system, and vehicle electronics. Engine operation is the result of perfect coordination between mechanics, thermodynamics, and electronics. #2. Main components of an automobile engine. An automobile engine consists of numerous mechanical and electronic components working together as a functional whole. Each component has a specific role and must operate in perfect harmony with the others. At the core of the engine is the engine block *, serving as the structural foundation that houses the cylinders. The block is usually made of cast iron or an aluminum alloy, depending on the required strength and weight considerations. Inside the cylinders are pistons which move up and down, directly participating in the combustion process. Pistons are connected to the crankshaft via connecting rods, transmitting the force generated by combustion. Pistons also have piston rings which seal the combustion chamber, control oil consumption, and transfer heat. Worn piston rings, are one of the most common causes of compression loss in older engines. The *** crankshaft is one of the most heavily stressed engine components. Made of hardened steel, it must withstand immense loads and vibrations. Its role is to convert the linear force of the pistons into rotational motion. The crankshaft rests on bearings that must be perfectly lubricated to prevent friction and wear. Above the cylinders lies the ** cylinder head **, which closes the combustion chamber. The head houses the * valves **, camshaft **, spark plugs or injectors, and air and exhaust passages. Valves control the intake of air and fuel as well as the exhaust of gases. Their opening and closing must be perfectly synchronized with the piston's position. The ** camshaft * operates the valves and determines their timing. Modern engines often use variable valve timing, improving efficiency across different operating conditions. The camshaft is driven by a timing belt or chain, and its failure can cause severe engine damage. The lubrication system includes the ** oil pump **, oil passages, and filters. Its job is to reduce friction, cool components, and prevent wear. Without proper lubrication, the engine would overheat and fail quickly. Equally important is the ** cooling system **, which includes the radiator, water pump, thermostat, and coolant. Modern engines also feature numerous ** sensors and electronic control units **. These systems monitor pressure, temperature, fuel mixture, emissions, and engine performance in real time. Thanks to these technologies, engines can operate more efficiently, reliably, and environmentally friendly than ever before. #3. Engine manufacturing process. The engine manufacturing process is one of the most complex industrial procedures today, requiring extreme precision, material control, and strictly defined phases. It begins with the design phase, where engineers define dimensions, tolerances, materials, and expected loads for every engine component. This is followed by material selection, typically aluminum or cast iron for the engine block, and specialized steel alloys for pistons, crankshafts, and camshafts. Materials must have precisely defined mechanical and thermal properties to withstand high temperatures, pressures, and vibrations. Next comes casting or forging the main engine components. The engine block is usually cast in molds, while components like the crankshaft are forged for higher structural strength. After rough shaping, each part undergoes CNC machining, removing material with micrometer-level precision. Cylinders, bearing surfaces, oil passages, and mounting surfaces are carefully machined. Following machining, components undergo heat treatment, such as hardening and tempering, to achieve optimal hardness and wear resistance. Cylinder and piston tolerances are critical, as even minimal deviations can increase friction or cause compression loss. Surface treatments, such as cylinder hunning, ensure proper oil film retention during operation. Quality control is crucial. Every component undergoes multiple inspections: visual, dimensional, and structural. X-ray and ultrasonic methods detect micro cracks or internal defects. Parts failing to meet standards are automatically removed from production. Once all parts are produced and inspected, engine assembly begins. This is done under strictly controlled conditions, often in clean rooms to prevent contamination. The crankshaft is installed into the engine block, followed by pistons, connecting rods, camshafts, and valve mechanisms. Every bolt is torqued to precise specifications, as even minor deviations can lead to severe damage. Finally, engines undergo rigorous testing on dyno benches. Various operating conditions are simulated, and oil pressure, temperature, vibrations, and emissions are measured. Only after passing all technical and safety criteria is the engine considered ready for installation in a vehicle. The entire manufacturing process reflects decades of development, engineering expertise, and industrial precision. Any mistake in this chain can have long-term consequences on engine reliability and lifespan. #4. Common engine faults and weak points. The most common engine faults arise from a combination of design limitations, usage patterns, and maintenance quality. One of the primary challenges with modern engines is their increased complexity, which introduces more potential points of failure. Today's engines operate at significantly higher temperatures and pressures than older designs, accelerating wear on certain components. Parts related to lubrication are particularly vulnerable, as even a brief interruption in oil supply can cause serious damage. A frequent issue is crankshaft bearing wear, often caused by poor quality oil, infrequent oil changes, or running the engine cold under heavy load. Piston rings also commonly fail, especially in engines frequently driven on short trips, where the engine does not reach optimal operating temperature. This leads to compression loss, higher oil consumption, and reduced power. Diesel engines are particularly prone to injector problems, as they gradually lose injection precision due to fuel impurities. Turbochargers are another common weak point, especially in modern downsized engines. Turbines operate at extreme speeds and temperatures and rely entirely on proper lubrication. Shutting down the engine immediately after heavy use can cause overheating and turbine damage. In gasoline engines with direct injection, carbon buildup on intake valves is a common issue because fuel no longer washes the valves as in older systems. The cooling system is also critical. Failures of the thermostat, water pump, or radiator can lead to overheating, often causing a warped cylinder head or head gasket failure. The head gasket is one of the most expensive and difficult repairs, frequently resulting from neglecting minor cooling issues. While electronics improve efficiency, they also introduce new types of faults, such as faulty sensors, ECU errors, and wiring problems. Most faults do not occur suddenly, but develop gradually over thousands of kilometers. Symptoms like unusual noises, increased fuel consumption, or reduced responsiveness are often ignored until serious damage occurs. In many cases, engine problems are not caused by poor design, but by a mismatch between the engine's technical requirements and how it is actually used. Modern engines demand discipline, proper maintenance, and understanding of their limitations, without which reliability quickly declines. #5. How to improve engine functionality, longevity, and efficiency. Improving engine performance starts with a change in design philosophy, not merely adding new technology. Today's engines are often designed to meet emissions standards and market demands, with long-term durability taking a back seat. A key step would be a return to more robust mechanical solutions, even at the cost of slightly higher weight or lower peak power. In the long term, a stable, lightly stressed engine achieves higher overall efficiency. Reducing extreme operating pressures and temperatures has a significant impact on longevity. Downsized engines with small displacement and high load often operate at the edge of material limits. Moderating specific power output substantially reduces wear on pistons, bearings, and turbos. Increasing oil capacity and improving lubrication systems also extend engine life and increase safety margins. Materials play a crucial role in future engine development. Advanced alloys, ceramic coatings, and surface treatments can dramatically reduce friction and wear. Reducing friction in the piston-cylinder interface is particularly important, as this is where most energy losses occur. Lower friction translates to higher efficiency, lower fuel consumption, and cooler operating temperatures. Adapting engines to real-world usage is another overlooked aspect. Most cars are driven short distances with frequent cold starts, whereas engines are often designed for ideal conditions. Installing smarter heating systems, such as electric oil or coolant heaters, could significantly reduce cold wear, extending engine life from the very first minutes of operation. Electronics should serve reliability, not just performance. Engine software could be set more conservatively to prevent overloading in unfavorable conditions. Adaptive systems that account for engine age, fuel quality, and driving style could automatically adjust operating parameters, reducing the risk of costly failures in older vehicles. Improving serviceability is also key. Engines should be designed so that critical components can be easily serviced or replaced. Many modern parts are hard to access, increasing service costs and discouraging preventive maintenance. Modular engine designs could significantly lower repair costs. Ultimately, true engine efficiency is measured not only by power or fuel consumption, but by total lifespan and reliability. An engine that runs reliably for 400,000 to 500,000 kilometers offers more real value than a high-performance engine requiring major repairs after 150,000 kilometers. The future of classic engines lies in a smart balance of technology, simplicity, and real human habits. #6. The future of internal combustion engines. The future of internal combustion engines, ICE, is not an abrupt end, but a gradual transformation with a shrinking role. Despite the strong push for electrification, conventional engines will not disappear anytime soon. This is due to infrastructure limitations, cost, raw material availability, and user habits. In many parts of the world, electric vehicles are simply not practical, leaving space for continued ICE development. One main direction for improvement is efficiency optimization rather than power increase. Technologies such as variable valve timing, variable compression ratio, and precise fuel injection already push efficiency boundaries. These innovations allow engines to operate closer to ideal conditions over a wider range of loads, reducing fuel consumption and emissions without drastic structural changes. Alternative fuels will increasingly extend the life of classic engines. Synthetic fuels, biofuels, and hydrogen can reduce emissions without replacing the existing fleet. Synthetic fuels are particularly interesting because they can be used in current engines with minimal modifications, though production is currently energy-intensive and expensive. Hybrid systems represent a practical compromise between conventional and electric powertrains. In hybrids, the ICE operates under optimal conditions, while the electric motor handles city driving and low-load scenarios. This significantly reduces engine wear and extends lifespan, while reducing fuel consumption without requiring large batteries. Regulations will play a decisive role in shaping engine futures. Emission standards are becoming stricter, often faster than technology can naturally keep up, resulting in increasingly complex, expensive, and failure-prone systems. Paradoxically, engines may become cleaner on paper but less maintainable in practice. In the long term, ICEs will likely remain in specialized applications: heavy vehicles, remote areas, industrial machinery, and markets with limited infrastructure. Their role will gradually narrow rather than disappear. The idea of a completely dead ICE is still far from reality. The future of engines will not be a victory of a single technology, but coexistence of multiple solutions. Success will depend on realistic approaches, not ideology or exaggerated promises. Engines that survive will be those that offer reliability, longevity, and real utility, not just impressive figures on paper. #7. Common engine failures, causes, and component lifespan. Engine failures usually result from prolonged wear and neglect rather than a single fault. Each engine component has an expected lifespan, which in real conditions is often shorter than manufacturer specifications. Longevity is most affected by driving style, maintenance quality, and operating conditions. Engines frequently started cold or driven on short trips experience significantly shorter lifespans for key components. Piston rings are among the first to show wear. They seal compression and control oil consumption, but gradually lose elasticity, typically between 200,000 and 300,000 kilometers, or earlier with poor maintenance. Symptoms include increased oil consumption, blue smoke, and power loss. Ignoring these signs can lead to severe cylinder damage. Crankshaft and camshaft bearings are highly sensitive to oil quality. Wear often begins subtly, but can result in complete engine failure. With proper maintenance, they may last over 300,000 kilometers, but with poor oil or infrequent changes, damage may occur by 150,000 kilometers. Typical signs include metallic noises and low oil pressure. Turbochargers are among the most stressed components in modern engines. Operating at extreme speeds and temperatures, makes them sensitive to improper shutdown and poor lubrication. Their average lifespan is between 150,000 and 250,000 kilometers, and turbo failure can cause additional damage, such as oil contamination of the intake or exhaust. The fuel injection system is another common source of problems. Injectors gradually lose precision due to deposits and wear. Diesel injectors often fail between 200,000 and 300,000 kilometers. Malfunctioning injectors cause poor combustion, increased fuel consumption, and additional stress on other components. The head gasket is one of the most expensive repairs. It usually fails due to overheating or delayed response to cooling system problems. When it leaks, oil and coolant mix, or compression is lost. This failure can occur even in engines with relatively low mileage if overheating is ignored. Timing chains or belts have limited lifespans, despite marketing claims. Timing belts are usually replaced between 90,000 and 150,000 kilometers. Chains may last longer, but poor designs can cause problems after 200,000 kilometers. Belt or chain failure almost always results in severe engine damage. Most serious engine faults could be prevented with early intervention and proper maintenance. Engines rarely fail, suddenly, without warning signs. Understanding the lifespan of individual components is crucial for realistic engine condition assessment and making informed maintenance or purchase decisions. *8. Proper engine maintenance and longevity. Proper engine maintenance is key to long and reliable operation, yet many drivers neglect it. Regular servicing, oil and filter changes, and checking the cooling system are basic steps. Oil reduces friction and wear on moving parts, and without it, the engine deteriorates quickly. Oil changes should be done regularly, with intervals depending on the engine type and fuel, but generally every 10,000 km for modern gasoline and diesel engines. Air and fuel filters are equally important. A clogged air filter reduces airflow and increases fuel consumption, while a dirty fuel filter can damage injectors and the fuel pump. For diesel engines, fuel quality is particularly important, as impurities can cause serious damage. Regular inspection and replacement of filters significantly reduce the risk of breakdowns. The cooling system is often neglected. The thermostat, water pump, radiator, and coolant work together to keep the engine at an optimal temperature. Engine overheating can lead to warped cylinder heads, head gasket leaks, or even engine block cracks. Regularly checking coolant levels and quality, as well as cleaning the radiator, reduces the risk of costly failures. Cables, sensors, and electronic systems are becoming increasingly important. Modern engines rely on precise sensor readings to optimize combustion and reduce fuel consumption. Faulty or damaged sensors can cause misfires, power loss, or increased emissions. Timely replacement or inspection of sensors prolongs engine life and prevents secondary failures. Regular inspection and tensioning of timing belts and chains are also crucial. Timing belt breakage or skipped teeth often leads to severe internal engine damage. Replacement of the belt according to manufacturer recommendations and checking chains on older vehicles is advised. Monitoring tension and wear reduces the risk of sudden failures. Driving style also affects engine longevity. Sudden acceleration, frequent start-stop cycles without warming up the engine, and long drives under heavy load with a cold engine accelerate were on pistons, bearings, and turbos. Driving according to conditions and gradually warming up the engine significantly extends its lifespan. Additional measures include occasional compression and oil pressure checks. These tests reveal early signs of wear on pistons, rings, or bearings before serious damage occurs. Monitoring oil and fuel consumption can also provide early warnings of potential problems. For maximum longevity, regular maintenance should be combined with high-quality fuel, oil, and spare parts. Even the slightest compromise on these components can shorten engine life. Ultimately, a regularly serviced, properly used, and monitored engine can easily last over 400,000 kilometers. *9. Electric and hybrid engines. Differences, advantages, and disadvantages. Electric engines operate on a completely different principle from internal combustion engines. Instead of burning fuel, they use electromagnetic fields to create rotation. This means they have no pistons, valves, crankshafts, or camshafts. The lack of moving parts makes them extremely reliable and almost maintenance-free. Electric engines also provide full torque from 0 RPM, resulting in strong and instant acceleration. The main advantage of electric engines is simplicity and efficiency. Energy from the battery is transmitted to the wheels almost without loss, whereas traditional engines lose a significant portion of energy to friction and cooling. Electric engines produce almost no noise and emit no exhaust gases, making them ideal for urban conditions and environmental standards. Hybrid engines combine the advantages of electric and conventional engines. In such systems, the electric motor assists with acceleration and city driving, while the internal combustion engine operates on longer trips or under higher loads. Regenerative braking allows energy to be returned to the battery, reducing fuel consumption and increasing overall efficiency. However, electric and hybrid engines also have limitations. Batteries are heavy, expensive, and have a limited lifespan. After several 100,000 kilometers, battery capacity significantly decreases, reducing vehicle range. Battery replacement is costly, often more expensive than most regular repairs on internal combustion engines. Electric engines also require complex cooling and battery management systems to prevent overheating. The electronics and software systems are intricate, and faults in them can immobilize the vehicle, which is a unique risk for electric and hybrid vehicles. In conventional engines, failures usually occur gradually and can be repaired in stages, while in electric systems, a failure can be critical. Nevertheless, the future of vehicles clearly points toward electrification. Emission reduction, better energy efficiency, and regulations push manufacturers to develop battery and hybrid systems. In cities, electric propulsion is more practical and cheaper to maintain in the long term, while conventional engines remain in specialized use, such as heavy vehicles or remote areas. Hybrid systems represent a realistic compromise, allowing the use of a conventional engine without overloading it. The internal combustion engine operates under optimal conditions, while the electric motor shares the workload. This reduces part wear and increases overall engine longevity. Energy management and intelligent systems become key to the reliability and economy of hybrid vehicles. Ultimately, electric and hybrid engines are not perfect, but offer new solutions to problems of traditional engines. While conventional engines require regular maintenance and careful use, electric and hybrid systems require monitoring of electronics and batteries. Understanding the advantages and limitations of each system is crucial for long-term efficiency and reliability. *10. Maintenance and servicing of electric and hybrid engines. Maintenance of electric and hybrid engines differs significantly from that of internal combustion engines. The biggest advantage is that electric engines have very few moving parts that wear out, so mechanical failures are rare. There are no pistons, valves, camshafts, or timing belts, which significantly reduces servicing costs. However, complex electronics, batteries, and management systems require careful monitoring. The battery is the most critical component. Its longevity depends on charging habits, temperature, and load. Frequent fast charging can reduce battery capacity within a few years, while proper maintenance and moderate charging extend its life. Hybrid systems often combine a small electric motor with a conventional engine, so the battery wears more slowly than in fully electric vehicles. Cooling systems for electric motors and batteries are equally important. Overheating can cause permanent damage and reduce efficiency. Electric vehicles use coolant and fans for temperature regulation, and in hybrids, the combination with an internal combustion engine requires additional monitoring. Regular checking of fluids and sensors is essential for longevity. Software maintenance is becoming an integral part of servicing. The ECU and BMS, battery management system, monitor engine and battery operation. Software updates often improve efficiency, reduce consumption, and fix errors. Regular monitoring and diagnostics allow early detection of faults before they become serious. The braking system, especially the regenerative system, also requires attention. Brake pads wear more slowly due to regenerative braking, but hydraulic components and sensors must remain in perfect condition. Regular inspections of brakes, including discs and pressure sensors, ensure safety and optimal system performance. Electric and hybrid vehicles also require inspection of electrical wiring and cables. Insulation damage, corrosion, or loose connections can cause short circuits and operational failure. Professional inspection and cleaning of contacts extend system life and reduce the risk of faults. Although electric engines are mechanically simpler, their complex combination of electronics and batteries means negligent maintenance can be very costly. Regular servicing, monitoring battery capacity, and diagnosing electrical systems are crucial for long-term reliable use. Hybrid systems require a combination of both approaches, maintaining the internal combustion engine and the electric drive. Proper maintenance ensures not only long vehicle life, but also optimal efficiency and economy. Electric and hybrid engines can last hundreds of thousands of kilometers with minimal repairs, but only if manufacturer instructions are followed and critical systems are cared for. Improper maintenance of batteries, sensors, or electronics can quickly negate all advantages of these engines. *11. Comparison of longevity and costs, conventional versus electric engines. Internal combustion engines have a predictable lifespan, but require regular and extensive maintenance. A properly serviced engine, with oil, filters, and consumable parts replaced, can operate between 300,000 and 500,000 kilometers. However, maintenance costs over this period are not negligible. Replacing gaskets, bearings, timing belts, and turbos can be expensive, especially on older or more complex engines. Electric engines, on the other hand, have far fewer mechanical parts that wear out, reducing overall maintenance costs. There are no pistons, valves, or camshafts, and brakes wear more slowly due to regenerative braking. The highest cost for electric vehicles is the battery, which typically lasts 8–12 years depending on charging habits and usage. Battery replacement can be expensive, but overall engine maintenance is much simpler and less frequent. Hybrid engines combine the advantages of both systems, but also their costs. Internal combustion engine components wear more slowly because the electric motor shares some of the load. Hybrid batteries are usually smaller, reducing replacement costs and extending their lifespan. Overall, hybrids offer a middle option, lower maintenance costs than conventional engines, but higher than purely electric vehicles. A key difference is how components fail. In conventional engines, failures are often gradual and can be partially repaired. In electric and hybrid engines, a battery or electronics failure can immobilize the entire vehicle, making urgent replacement critical. Therefore, diagnostics and preventive maintenance are even more important in electric systems. Fuel and energy costs also affect overall economy. Conventional engines consume petrol or diesel, and fuel prices fluctuate, adding to owner expenses. Electric motors use electricity, which is much cheaper in most regions, and regenerative braking further reduces energy loss. Hybrids use a combination, so fuel consumption is lower than conventional engines but higher than purely electric vehicles. Reliability under different conditions is another factor. Conventional engines can operate in extreme temperatures, remote locations, and without access to electricity. Electric engines depend on charging, and batteries lose efficiency in very low or high temperatures. Hybrids partially neutralize this issue, as the conventional engine can take over when the battery or electric system is not optimal. The full life cycle of the vehicle also includes repair, parts, and service costs. Statistics show that electric cars have lower average maintenance costs, but major repairs, especially battery replacement, can be expensive. Conventional engines have more frequent minor faults but are more predictable over the long term. Ultimately, choosing between conventional, hybrid, or electric engines depends on usage patterns, service availability, climate conditions, and the owner's financial capacity. Longevity and costs are not the only criteria. Practicality, reliability, energy efficiency, and real-world usability also matter. **12. Conclusions and recommendations for buyers and enthusiasts. Purchasing and maintaining engines, whether conventional, hybrid, or electric, requires a realistic approach and understanding of the technology's actual capabilities. Conventional engines still offer great flexibility and robustness, but require regular maintenance and careful use. Buyers should be aware of potential maintenance costs, especially for older vehicles or high-mileage units. Regular servicing, inspection of key components, and high-quality fuel or oil ensure long engine life. Electric engines offer simplicity and minimal mechanical maintenance, but require careful monitoring of batteries and electronics. Proper charging, cooling system maintenance, and regular diagnostics extend the electric drivetrain's lifespan. Hybrid systems combine the advantages of both, but also their complexity. Hybrid buyers should understand how both systems operate and how to properly maintain the engine and battery. For enthusiasts who enjoy DIY maintenance, conventional engines offer more opportunities for mechanical interventions and repairs. Electric and hybrid systems require professional diagnostics and often special tools and software. This means DIY repairs are not always possible, which should be considered when choosing a vehicle. A key piece of advice is to monitor the vehicle's actual condition rather than relying solely on mileage or manufacturer claims. Regular inspections, pressure and compression tests, and diagnostics help identify early signs of wear or failure. Ignoring small problems leads to expensive repairs and reduced engine lifespan. Buyers should consider how the vehicle will be used: city driving, long trips, extreme conditions, or a combination. Electric drive works best in urban environments and short distances, while conventional engines better handle high loads and remote locations. Hybrids offer a compromise, but with added complexity and maintenance cost. A reliable engine is the result of a balanced approach: quality parts, timely maintenance, and understanding technical limits. Buyers and enthusiasts should invest in knowledge and education about the engines they use. Only then can they maximize longevity, reduce costs, and avoid unexpected failures. The future of engines will depend on technological development, regulations, and user habits. Electrification and hybrids will not immediately replace conventional engines, but are changing usage, servicing, and long-term cost planning. Buyers must be aware of these trends and adapt their decisions accordingly. For enthusiasts, it is important to maintain a passion for engines and an understanding of their construction details. Deep knowledge of manufacturing, failures, maintenance, and new technologies enables rational decisions and long-term satisfaction. Engines are not just transportation. They are complex systems that require attention, knowledge, and discipline. In the end, the best approach is a combination of practical experience, regular maintenance, and awareness of trends. Regardless of the engine type, a buyer who understands how the engine works, what causes wear, and how to maintain it will achieve the best value, longevity, and safety. Only such an enthusiast can fully harness all the advantages of the technology, whether conventional, hybrid, or electric.